In this video, we're not going to talk about theory, we're only going to solve problems that have to do with definite integrals and the fundamental theorem of calculus. Before we start, let us revisit some results that we'll be needing in solving those problems, and let's start by the following property. Given a function f that's continuous on the closed and bounded interval ab, the definite integral that you see on the screen turns out to be the net area of the region bounded by the curve y equals f of x, the x-axis, and the two vertical lines x equals a and x equals b. That is to say, this definite integral from a to b fx dx is equal to the difference between a plus and a minus, where a plus is the area of the region just described above. So it's the area, we're talking about a plus, being the area of the region above the x-axis and below the graph of f, and a minus is the area of the region below the x-axis and above the graph of f. So on the picture, a plus is, this curve that you see here is the graph of f of x, and a plus would be the sum of these two pink pieces, right? Because a plus is the area of the region above the x-axis and below the graph. So we're talking about above the x-axis, below the graph. So we're talking about such a piece and such a piece. So what's a plus? It's the sum of these two pieces, right? The sum of those two surfaces. And then a minus is the area above the above the graph and below the x-axis. So in this case, I only have a piece as such, so a minus is going to be only this piece, right? So what's a minus? It's this surface. And it turns out that this definite integral is simply the sum of the areas, or the sum of the surfaces of the region above the x-axis and below the graph, chipping away from that sum the sum of the areas below the x-axis and above the graph of f. Okay? All right. And let's revisit these properties. So the integral from a to b n dx is equal to, so in this case, how would you describe it geometrically? This is the rectangle, right? This is the rectangle having width n and length b minus a. So it's going to be this product, n times b minus a. Obviously here n is supposed to be, talking about n being a constant, right? Part 2, the definite integral from a to b fx plus gx is equal to the sum of the two definite integrals, one that has to do with f and one that has to do with g, and the difference as well, right? And the third one, the definite integral of a dilation of the function is equal to this multiplicative constant n is a pure number here, pure constant, times the integral from a to b fx dx. So that multiplicative constant can be pushed outside the integral. Part 4, if you integrate over a point, of a continuous function, you're going to get 0. 5, if you reverse the bounds, if the upper bound becomes lower bound and the lower bound becomes upper bound, then there is a price to pay, and the price is just to have a multiplicative constant, in this case -1. So they are almost the same up to a change of a sign. And here's number 6. If you integrate from a to c and then you add that to the integral from c to b, so if you integrate from a to c then followed by c to b, this is the same as integrating from a to b, right? Okay. And the fundamental theorem of calculus, which has two parts. The first one, given, well, for both of them, we're supposing that f is a continuous function on the closed and bounded interval ab. Then the first one says this integral is equal to f of b minus f of a, where capital F, that you see here, is any antiderivative of the function f. Okay, so recall that. If you are trying to find this definite integral, it suffices to find any primitive function of little f, let's call it capital F, and you just evaluate capital F at the upper bound, f of b, and you subtract from that the evaluation of this primitive function at the lower bound, f of a. So you subtract f of a from f of b. That difference is the same as the net area that we talked above, above, right? Part 2 of the fundamental theorem of calculus is that if you define a function g of x to be as such, and this the x is the variable, right? So define g of x to be the integral from a to x, where x is between a and b, right? Because the function here is continuous between a and b. So if you take any x between a and b and you define g of x to be the integral from a to x f of t dt, that function turns out to be a continuous function on a and b, right? Because the input is from the range ab. That function turns out to be continuous there and differentiable on the interior of that set, so on the open AB. And the derivative, so moreover, the derivative of the function g of x is simply f evaluated at x. Okay, and this happens for any x between a and b. So not only g is differentiable, it has this nice formula. The derivative of this whole function, right? So the derivative of this whole function, g of x, is equal to f of x, correct? So you get this. All right, so let's go to the book and do some problems. All right, so this is on page 277. This is section 4.3, and let's do problems from the following, 13 through 22. Let's do a couple of them. So the question is to write a definite integral that represents the area of the region, and we do not need to evaluate the integral. Let's do 14. So we have that this function is, this black line is 6 minus 3x, and the region we're talking about is this triangle. All right, let's take a picture. Let's take the snapshot here. And paste it over here on this file. Okay. So this is, as we said, number 14. And this line is the function f of x equals 6 minus 3x. They gave it to us, right? I mean, we could have discovered it anyway, but they gave it to us. So they want a definite integral that represents this area. Well, as we know by this property over here, this definite integral, what is it? It's the net area in the sense that you subtract the sum of the areas under the graph, under the x-axis, from the sum of the areas above the x-axis. This is what we mean by net area of the region bounded by the graph y equals f of x, the x-axis, and the two vertical lines x equals a and x equals b. X equals a being that lower bound, and x equals b being this upper bound, right? Okay, so how about we have a comment here, since we're talking about a function that's non-negative. So if the function f is non-negative, which means there is no a minus. I mean, a minus would be 0, right? If the function is entirely sitting on one side of the x-axis. So let's talk about the non-negative side. So if the function f is above or at worst, touching the x-axis, right? So if the function is non-negative, then a minus would be 0 because there is no region below the x-axis. So as such, this definite integral would be just the area under the curve and above the x-axis, right? Which is the case over here. So it's below the curve and above the x-axis, right? And the two vertical lines are x equals 0 and x equals 2. So we get this integral. This area that we see here is the integral from 0, right? 0 to 2, right? And the function in this case is f of x. dx. Correct? And f of x in this case, we know what it is. It's 6 minus 3x dx. So we get this. Okay? Hope it makes sense. Let's move on to a different problem. So we just finished 14. How about about 18? So the function in this case is 4 divided by x2 plus x squared plus 2. Let's take this picture. And let's paste it here. So this is number 18. So this is number 18, and the function here, this is the function. The function they gave it to us to be f of x equals 4 divided by x squared plus 2. Okay. All right, so here we're talking about the vertical lines to be x equals -1, x equals 1. So these would be the bounds, right? So we are integrating from -1 to 1. The function is not negative, so that definite integral is going to be just the area below the curve and above the x-axis, right? All right, so -1 to 1, f of x dx. And f of x in this case is f of x dx. And as we said, f of x in this case is 4 divided by x2 plus 2, right? dx. Okay. All right. Another one. How about 21? How about 21? Okay, here slightly different. Let's take the picture. And paste it here. Okay. And they told us, this is 18, right? This is number 18, by the way. So this is number 18. Sorry, 21. 18 we just finished. And they told us that the function here is g of y is equal to y cubed, right? So g of y is equal to y cubed. So here the variable is y. The variable is y. It's not x anymore as it used to. So we're gonna integrate with respect to y, correct? So mentally think about this picture as a rotated picture where the vertical axis y, the y-axis, is actually the horizontal axis. Okay, to just contrast it with the previous discussions, just think about this as a rotated picture where this y-axis is a horizontal axis and the x-axis is the vertical axis. Okay, it's just renaming the variables here, that's it. So it's a dummy letter. All right, so and as such, if you think about this y-axis as a horizontal axis, the graph would be, or the area under discussion would be below the function and above the y-axis, and the y-axis is the horizontal axis. Remember, we're thinking about it, we're not doing it, we're not displaying it on the screen, right? Okay, so what's the lowest bound for y? What's the lowest y can get to, right? It's 0, correct? So the region, again, if you rotate it to have the y-axis as a horizontal axis, you're gonna see the 0 as one of the vertical lines, but they are displayed here as horizontal lines, a horizontal line. And the other one would be the upper bound for y. What's the largest the largest value y can take in this region is 2, right? Y would be 2. So it's from 0 to 2 then I'm integrating, right? From 0 to 2, and what am I doing? I'm integrating which function? The gy function, so the y cube function. The y cube function, right? So something like this. Correct? So what's the difference between this and the previous problems? The only difference is that they're renaming. Um, so in some sense, they are renaming the variable. Okay. So if they want to talk about the y variable here, so and they're drawing it as being the vertical axis, you have to rename it in some sense. And by this I mean rotate the picture. Okay, so rotate the picture so that the independent variable would be the horizontal axis and the dependent one would be the vertical axis. Okay, the independent here being y and the dependent would be x. Okay, all right, let's continue. 22 is very similar to that, so we're gonna integrate here with respect to y as well. Okay, so we're gonna integrate with respect to y as well, and the lowest y can get to is what, 0, right? And the highest it can get is 2. So this would be integral from 0 to 2 f of y dy. Okay, all right, so let's move on to the next set of problems. Evaluate the definite integral. So this is from 13 to 32, sorry, 23 to 32. Sketch the region whose area is given by the definite integral. So now we're gonna go back. They gave us what they were asking for here. They gave it to us in this case, and we have to describe the region that they are talking about, and then use a geometric formula to evaluate this integral. And then throughout this discussion, a is supposed to be positive and r is supposed to be positive. So whenever we see a and whenever we see r, they are supposed to be positive entities. All right, let's do one of these four. How about 26? So I have integral from 0 to 8 x over 4 dx. Okay, so this is problem 26. We go back to purple. So 26, integral from 0 to 8 x over 4 dx. Okay, so what's the function here? It's the function y equals x over 4. And how do you graph the function y equals x over 4? It's a line, right? It's a line. And in which what are the bounds? What's the lowest x in the in the described region here? What's the lowest x that we can reach is 0, and what's the highest x that we can reach is 8, right? So this is the region, this is the net area that's bounded by the graph y equals x over 4, which is this, y equals x over 4, so it's a line like this, passes through the origin, right? Okay, this is y equals x over 4, and the x-axis obviously, and the two vertical lines x equals 0 and x equals 8. So x equals 0. What's x equals 0? It's this axis. This is x equals 0, and x equals 8. This is x equals 8. So what's that region? What's that thing? So it's the net area that's bounded by the curve, the x equals 0 and x equals 8. Which one is it? So we're only talking about this portion, right? That's the area we're talking about, right? So this triangle, this is what this is equal to, right? All right, and this is a triangle. We know, and this obviously has a right angle here. We know how to find the area of such a triangle, right? It's base times height over 2. So let's find the base and let's find the height, and let's divide that product by 2. How much is this portion here? Let's say that this is the height. How much is this? This is 8, right? This is 8. Correct? And how much is this guy? How much is this guy? Well, what's this point? What is this point? Well, this point belongs to the graph of the function y equals x over 4 for input x equals 8, right? So when x equals 8, we get this height on the graph y equals x over 4. So when x is 8, how much is y? When x is 8, 8 over 4 is 2, right? So this is 2. So that's 2. Do you agree with me? One more time. To determine this base, the length of this base, it suffices to find that point here, right? And this point is the height of the function y equals x over 4 when the input is 8, when the input is this guy, 8. Correct? So because this point has two coordinates, 8 comma the y given by this function. Well, if the input is 8, the output is going to be 8 over 4, which is 2. Okay? So as such, what do we get? What's the area of this triangle then? So the area would be equal to, so this would be equal to 1/2 the height times the base. The height being 8, the base is 2. Okay, this is easy. This is 8, right? So if you evaluate this, you get 8. If you use the fundamental theorem of calculus, you should also get 8, right? How about we actually do it using the fundamental theorem of calculus? So a different approach. They're not asking for this, right? They're not asking for this. So a different approach. But it doesn't answer the question. It doesn't answer the question. So let me be very clear. Which does not answer the question. Why? Because they told us to use geometric formula to evaluate the integral. So we cannot use the fundamental theorem of calculus, but I'm still gonna do it just to make sure that you understand that we should get the same answer. Okay, we're gonna get the same answer as we should. So which does not answer the question. Okay. All right, let's do it. Well, we have the integral from 0 to 8 x over 4 dx. Okay. And x over 4 can be thought of as 1 over 4 times x dx. Correct? And remember one of these properties that we talked about here? You see this m, the multiplicative constant? You can push it outside. You can push it outside the integral, right? You can push it outside. You see it? I'm going to push the 1 over 4 as a multiplicative constant outside. So this would be equal to 1 over 4, the integral from 0 to 8 x dx, right? Now the fundamental theorem of calculus, part 1, let's revisit that. Fundamental theorem of calculus, part 1, it tells us if f is continuous on AB, so in this case x over x is continuous between 0 and 8, then if you find any primitive function of little f, in this case f is x over 4, then that's how you find this definite integral. It's any antiderivative evaluated at the upper bound minus that antiderivative evaluated at the lower bound. Correct? So I'm going to apply it. So we're going to apply, So we're going to apply the fundamental theorem of calculus, part 1. How about FTC for fundamental theorem of calculus and part 1? So the 1 over 4 is still there. How about we find an antiderivative of x? How about we find an antiderivative of f? Let's erase this and explain all this. So an antiderivative of f is so primitive function of x in this case. The function is x. Is previous section, right? The previous section tells us this is x to power 1. A primitive of x is x to power 1 plus 1. So x of x to power 2 divided by 1 plus 1, which is 2. plus any constant, correct? So where c is any constant. So where c is any constant, this would be an antiderivative. So this would be a function f of x. This would be a function f of x, capital F of x. So let me call this capital F of x, right? What's capital F of x? It's that primitive that we are talking about for a particular c, and c can be any real number, correct? And what does it say here? It's what does the fundamental theorem of calculus part 1 say? It says, well, evaluate capital F at the upper bound, so which means you evaluate capital F at 8, and you subtract from that the evaluation of f at 0, correct? So this is what the fundamental theorem of calculus part 1 says. You find an antiderivative function f, in this case is x squared over 2 plus c. You choose the c, right? You choose the c, and you do the subtraction, right? And you do the subtraction. And what is this? What is this? This is equal to 1 over 4. Well, f of 8, what's f of 8 if you take this guy? F of 8 is going to be 8 squared over 2 plus c. This is f of 8, right? This is f of 8. Replace x by 8, you get this? And minus f of 0. F of 0, and what's f of 0? It's 0 squared over 2 plus c. Am I correct on this? So f of 8 is, you take this primitive, you evaluate it at 8, you get this. And f of 0, you take this primitive function, you evaluate it at 0, you get this. Alright? And what do you get? Well, I hope you see that the c's cancel. I hope you see that the c's cancel. And this is always the case, right? Because f of b minus f of a, f of b minus f of a in the fundamental theorem of calculus, you get f of b minus f of a, right? This is going to have the constant c, and this is also going to have the constant c. The same constant c, since we're talking about subtraction, that c is going to cancel. That c is going to cancel all the time, not just in this particular context. That c is going to cancel. So how about from the get-go, we choose c to be 0, since we can find, we can, the fundamental theorem of calculus part 1 tells us any primitive function we can choose, right? Any primitive function. How about we go for c being 0, so we don't have to carry these c's, and at the end of the day, they're going to cancel anyway, right? Okay, so in the future problems, I'm going to just cancel this c. Okay. In the sense that I'm choosing c to be 0. All right, and what is this? This is 1 over 4. 1 over 4. 64 divided by 2 minus, what's 0 squared over 2? This is 0, correct? And that's 1 over 4 times 32. Why? Because 64 over 2 is 32, and this is simply 8. Okay, and this is the same result as we found in the different approach, which is of geometrical flavor, right? We just solved it using geometry here. All right. Back to our book here. Next page. 278. Let's choose one of these problems from 27 to 32. How about solving, let's choose these two, 30 and 32. Okay, let's do 30. So primitive or definite integral from minus a to a of the function a minus the absolute value of x dx. Okay, so this is problem 30. Minus a to a minus absolute value of x dx. Okay, let's take this function. Let's try to graph this function a minus absolute value of a. How do you graph up a minus absolute value of a? Well, if you think about it, minus absolute value of a means you are reflecting the absolute value function in the x-axis, right? In the x-axis, because of the presence of minus, and you are shifting it vertically an amount of a, right? And remember in the book they said on the previous page, they said a is positive, right? You see this? They said a is positive. So so the a that you see in this problem, in number 30, is positive. So back to this. How do we get a minus absolute value of x? We graph absolute value of x. We multiply it by -1, which means we are reflecting absolute value of x in the x-axis, and then we are shifting it vertically upward a units. Correct? So we get something like this. These are transformations that you learned in college algebra. Okay. So at the end of the day, we're gonna get the absolute value function upside down because of the presence of minus, and shifted up a units. So this is y equals a minus absolute value of x. And what is this guy here? That's a. Correct? This is a 90-degree angle here. Okay, it's not reflected in the picture, but this is 90 degree. All right. And they want to integrate this function between minus a and a. Between minus a and a. Where is minus a on the picture? How about we think about this point? What's that point? What's that point here? And this point. These are the x-intercepts of the function, of this function, right? The x-intercepts. And the x-intercept correspond when the function vanishes, correct? When this function vanishes. Let's do some calculations here and to see where this function is vanishing. Where does this function vanish? Where is y equals a minus absolute value of x equals 0? Where does this equal 0? Well, this equals 0 as long as the absolute value of x is a. And since a is positive, right? That means that this happens when x is plus. This happens when x is plus or minus a. Correct? So these are those guys. So plus and minus a. Okay. All right. So back to this. To the definite integral. This is the net area of the curve y equals a minus x, minus absolute value of x. So this graph, so it's bounded by this, the x-axis, and the two vertical lines, x equals minus a and x equals a. So which part are we talking about? So the curve, the x-axis, and the two lines, x equals minus a and x equals a. So we are talking about this triangle here, right? So we're talking about this triangle here. So this is that, right? It's this triangle. All right, and what's this? What's the value of this? What's the not the value? What's the area of this triangle? Well, this triangle is obviously symmetric with respect to the y-axis. Correct? So it's twice one of them. It's twice one of them. Okay. And what's one of them? What's one of them? What's the area of one of them? How about we find this piece? So that's gonna be twice, two times this area. Correct? And what's this area? It's height times base over 2. Height times base over 2. So it's 1/2. Okay. So it's 2 times the area. I'm talking about the area now. Half height times base. And how much is the height? Is a, right? And how much is the base? Is a. Correct? Agree with that? So this is a and this is a. So it's going to be a times a over 2. That's the area of one triangle. So the area of the full triangle is a squared, because the half and the 2 cancel each other. So this is a squared. Make sense? All right. Now, if you are curious on how to do it using the fundamental theorem of calculus, let's do that. Let's do that, even though it doesn't answer the question, but it's good to see it. So, alternative approach. Using fundamental theorem of calculus part 1, which again, it doesn't answer the question because they want us to solve the problem using geometrical approach as we did above. But I'm gonna do it a different approach just to get used to how these things are intertwined. So what's the question again? It's this minus a to a minus absolute value of x dx, right? Okay, so this is this picture. This is this picture. And what are these? I mean, this is the absolute value function, we know that, but it has two pieces, right? It has two pieces. It has two pieces. So it has this piece when x is between minus a and 0, and it has this piece when when x is between 0 and a. Correct? So it has two pieces. That piece, let's do it in red. This piece when x is between minus a and a, and that piece when x is between 0 and a. Agree with that? All right. So because of one of the properties, let me tell you which one, part 6, because of property 6, I can split, right? If you go from a to b, I'm going backward, right to left. If you are going from a to b, you can go from a to c plus integral from c to b. Okay, and c can be any number. In particular, it can be a number between a and b, right? Remember this property? So c can be any number. You know what c I'm gonna choose here? I'm gonna choose c to be 0, right? Because the curve changes from being that piece to that piece. Okay, and how about we actually talk about each piece? What is this piece? What is this piece? This is when x is positive, right? Or non-negative. What's the absolute value of x if x is non-negative? What's the absolute value of x if x is non-negative? It's x, right? So that piece is y equals a minus x. Agree with that? Remember, absolute value of x by definition is x if x is non-negative. And here on this side, on this part of the graph, x is non-negative because it's on the positive side of the x-axis. So the absolute value of x is x. Now how about this? Here x is non-positive, it's on this side of the x-axis, so the absolute value of x is negative x. So what's this then? This is y equals a minus the minus x, right? Because the absolute value of a negative number or non-positive number is minus that number, correct? And what's a minus the minus x? Isn't it a plus x? Isn't it a plus x? Right? So what's this line at the end of the day? This is a plus x. Okay? All right, so as I promised, we're going to split the integral. We're going to split the integral. We're going to go from minus a to 0 to 0. A minus the absolute value of x, in this case, plus x, right? So plus x dx plus, let me take it here. Oops. So plus the integral from 0 to a of the function, this function. But how much is this function when x is positive? It's a minus x. It's a minus x, right? Dx. So one more time, what did I use here? I've used property 6 above. You split this, you can stop anywhere. Anywhere. I stopped at 0. I stopped at 0. Why? Because this function, absolute value of x, changes at 0, right? Below 0, absolute value of x is minus x. As such, I can replace absolute value of x by negative x, and this becomes minus the minus x, so plus x, as discussed above. And after 0, the absolute value of x becomes x. So this becomes simply this. Make sense? Okay. All right. And these are gonna be two entities. Let's call this, let me change color here. How about we call this I, and we call this J. Okay. So we want to find each one of them and add them up. Let's find I. So I, as we said, is minus a to 0, a plus x dx. Correct? All right, now we go to probably property 3 or 2. Integral of a sum is the sum of the integrals, right? You can split sums. So integral is a linear operation. So you can split sums. You can get minus a to 0 a dx plus minus a to 0 x dx. Correct? We can get this. Why? Because the integral of a sum is the sum of the integrals, right? Makes sense? Okay, let's find each one. This is by property 1. By property 1, let me label this. This is by property 2 here. This is by property 6 here. And now by property 1, what can I write? By property 1, I can write the following. A times 0 minus the minus a. And let me explain why. Because property 1 says integral from a to b n dx is n, right? Property 1, remember? N b minus a, right? B minus this guy, upper bound minus lower bound. In this case, upper bound is 0 minus the lower bound, which is minus the minus a. Makes sense? By property 1. Okay, one more time. Let me take you back to property 1, so probably facilitates things. You see this? Integral from a to b n dx is n times the quantity b minus a, upper bound minus lower bound. So in this case, n is, in our case, n was a, so this guy is a. B is 0, and little a is minus a. So what do we get? We get what? We get n times the quantity upper bound, which is 0, minus lower bound, which is minus a. Correct? We get this for this guy. For this piece, plus, how about I make some room for this? So plus what? By the fundamental theorem of calculus, I just need to find a primitive for x, which is x squared over 2, right? X squared over 2 plus a constant. I'm going to take the constant as 0 as we discussed before, because I'm going to take the subtraction here, and that's going to take care of the c. It's going to cancel the c, right? So it's going to be f of 0, f at the upper bound, which is 0, minus f at the lower bound, which is minus a. Correct? And what's f? Where f is any antiderivative of the function x, and I can take it to be x squared over 2 plus a constant. As we said, we're going to choose the constant c to be 0, right? Okay, so that's going to be then equal to what? All this is a squared. All this is a squared, because this guy inside is a. A times a is a squared, plus, let's see what this quantity is. f of 0, well, f of 0 is 0 squared over 2, minus f of negative a. Replace x by negative a. You get the square of negative a divided by 2. Correct? The square of this is a square here. This is a square here of negative a divided by 2. Okay, and that thing is equal to a squared plus that thing is minus, right? This is 0 minus a squared over 2. Okay, and what's a squared plus minus? Plus minus means you are subtracting. If you add the opposite, means you're subtracting. A squared minus half of a squared is half of a squared, right? You get this. Okay. And I hope you start realizing what's going on. What did we find here? We found without geometry, we found 1. And what's 1? What's the geometric interpretation of 1? This is the triangle. This is the triangle to the left, right? This is the triangle to the left. And as we said in the geometrical aspect, we said that each triangle is half the entire triangle, right? Each piece here, because of the symmetry, each piece is half of the full thing. And what's half of the full thing? It's half a squared, right? Which we found over here, right below. Correct? Because the full thing is a square. We found it in using just geometry. Okay. All right. This is 1. Or more precisely, this is I. Now we still need to find j. We still need to find j, and then we're gonna add them up. So j is the integral from 0 to a minus x dx. Any guess for j? J is gonna be the same as I, right? Because this is the area of this triangle. We're gonna find the same as we found here, which is half a squared. But the point is, sure, geometry here is way simpler than doing it just using fundamental theorem of calculus. But the idea is we're gonna, because here the shapes, the geometrical shapes that we get are very easy to, we know we have formulas for these shapes, right? Triangles and so on, rectangles. But what if this function in the future, we're gonna see functions that are crazy here, and we don't have a formula for that geometrical shape. Okay, so I'm kind of like training you in some sense, the easy case, so you would appreciate it more in the more complicated case. So j is integral from 0 to a minus x dx. Let's do it. We know the answer, right? The answer is already here. So j is the integral from 0 to a of a minus x dx. All right, the treatment is very similar as we did here above, right? What did we do here? We split, right? We split the sum. Here a difference, but property 2 tells us that we can also split the difference. So we're gonna write from 0 to a dx minus 0 to a x dx, right? Okay. If you want to use property 1, you can use it. We used it above. This is very similar to this, right? So very similar to this discussion. How about we use, instead of using property 1, how about we use the fundamental theorem of calculus to do both of them, actually. Okay. What's a primitive function for a? What's a primitive function of a? A is a constant, right? So a is a constant. What's a primitive for a constant? If you are integrating with respect to x, right? The variable is x. So a is a constant. And what's a primitive for a constant a? As we found in the previous section, this is ax, right? So this is a primitive function for a. So it's ax. And how about we give it a name? So how about we give this guy a name? This is g of x. So that's gonna be g of upper bound minus g of lower bound, right? It's gonna be a primitive of a. That's a primitive of ax, because if you differentiate this guy, you get back a, right? If you differentiate ax, you get a. So that's a primitive. We can add a constant, but again, don't add a constant because they're gonna cancel each other after you subtract g of a. If you subtract g of 0 from g of a, that thing is gonna cancel the constant. So why in introducing a constant, and we know it, they're gonna cancel each other, right, at the end of the day. So the constant is not gonna intervene at the end. So how about throwing it away from the get-go? All right, so we get this minus we're talking about this definite integral now. So f of upper bound, which is a, minus f of lower bound, which is 0. This is fundamental theorem of calculus again, right? This is fundamental theorem of calculus here, part 1. Part 1, correct? Okay. What's f? So what's f? It's any primitive function of x, right? It's any primitive function of x. What's a primitive function of x? X squared over 2. We talked about this above. And you can add a constant again, but since they're gonna cancel each other, how about taking that constant to be 0? Very good. So j would be this, right? We're gonna evaluate g at a, subtract from that the evaluation of g at 0, and then we're gonna do the other part. So let's do it. So j is equal to g of a. What's g of a? Is a times a, so a squared, minus g of 0. What's g of 0? Is a times 0, which is 0, minus f of a. F of a is a squared over 2, minus f of 0. And what's f of 0? Replace x by 0, you get 0, right? Okay, so this is then a squared minus a squared over 2, which is as expected, a squared over 2. Okay, so j is the same as I. Is the same as I. This was I, right? So at the end of the day, what's this integral then? It's I plus j, which is half a squared plus half a squared. The sum is gonna be a squared, as found before. Again, no doubt this is a way better approach, but the only reason it's a better approach because you have formulas for areas of a triangle. This is the main thing. This is what was the engine in this discussion, right? Remember this thing here? That's the area of that triangle at the time. But in the future, the functions are not gonna be lines anymore. So if it goes crazy, you don't have formulas anymore, right? So you are on your own, and by your own I mean you're gonna have to use the discussion that we did below. There's no shortcut. There's no shortcut anymore. Okay. All right. So I introduced it here just for you to see it. Okay. All right. This is the alternative approach. Let's keep going. How about 32? As I promised you earlier. So we're gonna integrate the function, the square root of r squared minus x squared dx between minus r and r. So 32. We're gonna integrate between minus r and r the square root of r squared minus x squared. And remember what they told us? They told us that r is positive, right? They told us that r is positive. Okay. What's this function? Is it a nice function? Square root of r squared minus x squared. If it's not a nice function, I don't know how to integrate it using. I don't know a. Okay, I should say I don't know how to integrate it using fundamental theorem of calculus, because I don't know a primitive function for the square root of r squared minus x squared up to this point. Okay, we haven't learned how to find such a complicated or more complicated looking function. We didn't learn how to find a primitive for such a complicated looking function, right? Okay. So what's this function? How do we graph square root of r squared minus x squared? Well, do you remember how r is positive? Do you remember this what this guy is? X squared plus y squared equals r squared. What is this? This is the equation of a circle centered at the origin and of radius r, right? So this guy is a circle centered at the origin and of radius, okay, maybe this is better. Maybe this is centered at the origin, okay. So this is centered at the origin of radius r, right? So this radius, oops. So this radius here is r, right? Okay, but this is not what we have. What we have is, if you solve for y in this equation, we get y squared equals r squared minus x squared. So we're getting closer and closer to this, right? And this means that y is plus or minus the square root of r squared minus x squared if we take x to be at most r, or if we take x to be between minus r and r. This would be a non-negative entity. As such, we can solve this equation for y and get this. Okay, and what does it mean? So this means we have two functions. So y, or there are two functions here that were given implicitly by this equation, and those functions are plus and minus square root of r squared minus x squared, right? There are many other functions given by this implicit formula or this implicit equation, but the most conspicuous ones are the plus square root and minus square root. What does it mean? It means either the upper half circle, or the lower half circle. Okay, the plus corresponds to the upper one, and the negative corresponds to the lower one, as you know. Okay, I'm just refreshing your memories. So this upper one has equation y equals square root of r squared minus x squared. Okay. All right, I don't like this writing. So how about this? So this upper half circle is y equals square root of r squared minus x squared, and the lower one is the minus, y equals minus square root, right? In this case, they gave us this one with a plus sign, so they're talking about the upper half circle. Make sense? So it's not the lower one. Let's erase it then. It's the upper one. Very good. And let's erase all this discussion here. Okay. All right. So we know the function now. We know the function, and they told us we should integrate x between minus r and r. So between minus r and r, what does it mean? It means that we are talking about the x equals negative r as being the lower one. Remember, this point is r because this is the radius, right? And x equals r as being the upper bound. Makes sense? So what are they talking about then? What is this? What is this then? This is the net area. In this case, since this is non-negative, this whole thing is then the area under the curve y equals square root of r squared minus x squared, and above the x-axis, and bounded by x equals minus r and bounded by x equals r. So what's that area then? Isn't it this? Isn't it this one? That's this area, right? Okay. And what is that? What's the area of this upper half disk, right? It's a disk. What's the area of this upper half disk? Well, it's half The area of the entire disk. And what's the area of the entire disk? It's pi times the square of the radius, correct? So it's pi times the square of the radius. Makes sense? So 32 is simply this. Okay, so that's 32. Let's keep going. How about the problem here? So over here they said in exercises 33 through 40, evaluate the definite integral using the values below. Okay. Let's choose, how about we choose 40? How about we choose 40? So they gave us those guys and they want us to find 40. Let me copy the details on the screen. So as we said, this is number 40. We have, so I'll tell you what we have. We have that the definite integral from 2 to 6 of x cubed dx is equal to 320. They also told us that the integral from 2 to 6 x dx is equal to 16, and the integral from 2 to 6 dx is equal to 4. Okay, try to actually on your own try to come up with these values on your own by using the fundamental theorem of calculus part 1. Okay, right, so you take the any antiderivative of x cubed, which is, forget about the constant, let's take the basic one, x4 over 4 evaluated at 6, subtract the evaluation at 2 from the evaluation at 6, you should get 320. Very similar, similar discussion here. Antiderivative of x squared over 2. Evaluate this at the upper bound and subtract from this the evaluation of x squared over 2 at the lower bound. Over here it's going to be 1 times b minus a. 6 minus 2 is 4, so this is 4 easy, right? Okay, they told us these anyway, and they want us to find the integral from 2 to 6, 21 minus 5x minus x cubed dx, right? They want us to find this guy. Okay, so this thing is the same as, because you can, integral commutes with addition and subtraction, so in this case I have subtractions, so I can split this and get this 21 dx minus integral from 2 to 6 5x dx minus the integral from 2 to 6 x cubed dx. What did I do here? I applied property 2 above, right? Property 2 above. Makes sense? Okay. And what is this guy? 21 is a constant. I can think about 21 as 21 times 1. I can push out the 21 outside because of one of the properties. I think it was property 3. Let me go back and convince you that this was 3. Let me see. Yeah, it was property 3. You see this? Property 3. You can push out multiplicative constants. The function f of x in this context is 1 for the first integral, right? Okay, let's go back. Let's go back to our page over here. So I can push out the 21 to get a 1 inside. So 2 to 6, 1 dx. Okay, but typically people don't write the 1. They kind of like have an abbreviated notation. So this thing is the official notation or the official writing, but if you erase the 1, that's a notation for the other one that I just erased. Okay, so this guy means the integral from 2 to 6 of the function 1 dx. So the integrand is 1. Okay, but people write it this way as a notation for the previous one. Okay, All right. Minus 5 is also a multiplicative constant. I can still push it outside. So you get 5 integral from 2 to 6 x dx minus integral from 2 to 6 x cubed dx. Correct? And why is that? Because of property 3, as we said. Property 3. Okay. Very good. Now, do we have this guy? Do we have the integral from 2 to 6 dx? They told us this is 4. This is 4, right? So they told us that this guy is 4. Did they tell us this? Integral from 2 to 6 x dx? Yeah, it's the 16. It's the 16. And this guy here is the other one, which is 320. Okay. So this is 320. And then I'll let you finish this. This is how much? 21 times 4 minus 5 times 16 minus 320. All right, I'll let you finish this on your own. Just do the math here, just the algebra, okay? All right. Back to the book. Okay, so these are very similar. Still very similar, right? And let's do, how about we do 44 orally? Using properties of definite integrals, given that the integral from minus 1 to 1 fx dx is 0. How about I zoom in so you can see it through the video? I'm talking about 44. Okay? So using properties of definite integrals, given the integral from minus 1 to 1 fx dx is equal to 0, and the integral from 0 to 1 fx dx is equal to 5. So we know these guys. Evaluate the integral from minus 1 to 0. The integral from minus 1 to 0 fx dx. Alright, how do you think I'm gonna do this? Part A. Actually, I'm not gonna do it orally. I'm gonna do it using the notebook, this one. So that's 44. We are given that the integral from minus 1 to 1 fx dx is 0. And we are given that the integral from 0 to 1 f of x dx is equal to 5, right? So we're given these things. And they want us to find, for part A here, they want us to find the primitive, or the integral from minus 1 to 0 f of x dx. This is what they want us to find. Okay, so how about we think about this? Minus 1 to 1. What's integral from minus 1 to 1 fx dx? Based on property 6, let me take you back to property 6 just quickly. Property 6. Remember property 6? If you integrate from minus 1 to 1 from a to b, you can have a rest station in some sense anywhere at any point c. At any point c. It can be between a and b, and it can be away from a, I mean, it can be outside of the interval a, b, correct? That point c. Well, let's see where should I split the sum? What should c be here in my context? Where should c be in my context? What do you think? I mean, apparently it should be 0, right? The only other information I have is when the bound is 0. So how about we split this at 0? So we get minus 1 to 0 fx dx plus the integral from 0 to 1 fx dx. Why is that again? This is by property 6. Correct? Okay. So and do we know any of these? Do you know this? Yeah, that's 0. That guy is 0. So this guy here 0, we're given that, right? It's at the top of the screen. So 0 is equal to, do we know this? No, that's the one we need to find. That's the one we need to find. And how about this? Do we know that guy? Yeah, it's 5, right? That's 5. So that's 5. Okay, so can we solve for this guy? Oh, I forgot to write the x. So can we solve for this guy then? The desired thing? Yeah. So that guy should be -5, right? That guy should be -5. Agree with this? So that's part A. Part B, maybe now we can do it orally. So now we know this guy. Now we know this guy. How much is this? This is -5. So part B is gonna be, they want us to subtract what we just found in part A from 5. This guy's 5, right? So it becomes 5 minus what we just found in part A, which is -5. So this becomes 5 minus the -5. So 5 plus 5. So this is 10 then. So this is 10, right? Okay. Part C, again, I'll continue this orally because it's almost done. I mean, we don't need to write anything. Everything is on the screen now. Integral from -1, 1, 3 fx dx. That 3 is a multiplicative constant. I can push it outside based on property 3 in our discussion. So if you push it outside, then you get the 3 outside -1 to 1 fx dx. And what's that -1 primitive or integral from -1, 1 fx dx? Isn't it 0? So this is 3 times the 0, right? Because you push this 3 outside, and once you push it outside, you get 3 times this integral, and then 3 times 0 is 0. So this guy is 0. Part D, the integral from 0 to 1, 3 times f of x dx. Still, that 3 is a multiplicative constant. You can push it outside. So this becomes 3 times this integral. And 3 times this integral, and the value of this integral is 5. So 3 times 5 is 15. So part D tells you what we just found, that part D is actually 15, right? Okay. All right. Let's do one more here. How about 52? If function f is defined below, so it's given like this. So this is the function, and they want to use geometric formulas to find that thing, that integral from 0 to 12 fx dx, right? Okay, so let's copy that. So this is number 52. We're given that f of x is equal to 6 -1/2 x plus 9. So that's 6 when x is bigger than 6, and it's -1/2 x plus 9 when x is at most 6. Okay, so and again, they want the treatment here to be just geometric. All right, no problem. Let's use geometry, which means we need to graph this function. And how do we graph this function? Well, it has 2 pieces. This function is 6 if x is bigger than 6. How do you graph the function 6? It's the horizontal line. So it's a horizontal line. This is the function y equals 6, right? But they don't want all of it. They don't want all of it. They want just the piece corresponding to inputs bigger than 6. So we're gonna erase the piece that doesn't correspond to these inputs. Okay, so we're gonna erase that. All these inputs correspond to negative, all these outputs correspond to negative inputs. I'm gonna keep erasing until I get to input 6. and input 6. Oops, what happened here? So I'm gonna keep erasing as we said, all the way to input 6. What's going on with this? Okay. I have no idea what's going on. All right, anyway, so that's for input 6. And here I have a hole, right? It's a hole because the function is not at altitude 6 anymore when input is 6. It's gonna be at that altitude, and we're gonna figure out what this altitude is. Moving on, so this is the 6 guy. Moving on, we're gonna now go to inputs that are at most 6. So we're talking about inputs from this side of the x-axis, this side, left side of 6, right? And those input have outputs following this recipe, minus half x plus 9. How do you graph minus half x plus 9? This is a decreasing, this is a line with negative slope, right? With negative slope. So it's a decreasing one with y-intercept being 9, right? With y-intercept being 9. So it's going to be a decreasing one with y-intercept being 9. Okay. I'm going to take this picture and drag it all the way here. Okay. So we are talking about y equals negative half x plus 9. The y-intercept is 9, so it's somewhere here, and it's going to keep decreasing. We want this for x less than or equal to 6, right? What happens when x is 6? When x is 6, what's the y value? What's the y value when x is 6? Well, when x is 6, that's going to be minus half times 6. What's minus half times 6? Is minus 3, right? So one more time, when x is 6, that's going to be minus half times 6. And what's minus half times 6? Is minus 3 plus 9. Minus 3 plus 9 is 6, right? So the function actually is going to be a function that's going to complete this whole. So it's going to be a whole, that function is going to output 6 when the input is 6, right? Because we just did the calculation. And then it's going to come from this side, right? Something like this. And the y-intercept, as we said, is 9. This is a 9 here. Make sense? Okay. Okay, so very good. So what do they want? They want us to find the integral from 0 to 12 f of x dx. Okay. Pictorially, what are they talking about? So they're talking about the function. This function f of x, this is f of x, right? This is f of x. They're talking about this function, or the area bounded by this function. It's a since the function is non-negative, the area is above the x-axis, and bounded by the line y equals 0. That's the line y equals 0. And the line y equals 12. That's the line y equals x equals 12. Did I say y equals 12? I meant x equals 12. So x equals 12. Okay. So what's that area then? It's this area here, right? It's this area here. Okay. All right, so the question becomes, how do I find this area? Using geometry. They told us to use geometry. Don't use the fundamental theorem of calculus. All right. So we're gonna split it into shapes that we know how to, or we have formulas for. And look at this. This you can complete here this triangle. You see, rectangle. You see this rectangle here? So this blue region can be split into this pink region and this green region. This pink region is a rectangle, and this green region is a triangle. And we add them up, we get the blue region, which is that guy, right? So turns out to be not a bad problem once you have the graph. All right, let's talk about the pink region. What's the pink region? This is a rectangle. How do you find the area of a rectangle? It's width times length, right? So what is it? How much is this? How much is the width? In order to do so, actually it's explained here. How much is this distance? I'm talking about this distance over here. How much is this? This is 12, right? So this guy is 12, right? Because it's between 0 and 12, so this is 12, no doubt. And how much is this guy? How much is this guy? It's 6, isn't it? It's 6. So it becomes 12 times 6, right? Which is 72. Just a second here. So this is 72. So this area is 72. Makes sense? Okay, how about the green area? This area here. Well, what's this number? This guy is 6, right? It's at the same height as all these points, so this is 6. So how much is this length? So how much is this length? It's 9 minus 6, which is 3, right? Okay. And now, how about this length? How about this length? Well, this length is 6, right? Because the x-coordinate of this point is 6 and the x-coordinate of this point is 0, right? This is 0 here. So this length then is 6 minus 0, which is also 6. Okay, actually let me write it here. Make sense? All right, and as such, what's the green area? What's the green area then? Well, the green area is half times 3 times 6. Do you agree with that? It's half times the height times the base, because this is a right angle triangle, right? Right angle triangle. The height is 6 and the base is 3. So half the base times height is half 18, which is 9. Okay. So long story short, this blue region, there's no blue anymore, unfortunately, here on the screen, but this blue region, by blue I mean green combined with pink, is the 9 plus the 72. So it's the 9 plus the 72, which is 81, right? Okay. So that's this. You can use the fundamental theorem of calculus to do it, even though they didn't ask us to do that. But try it on your own. If you want to use the fundamental theorem of calculus, you're going to go 0 to 6. I mean, you're going to split this guy 0 to 12. You're going to split it between 0 to 6 and 6 to 12. Why? Because at 6, the function changes from being that thing, which is minus half x plus 9, to being that thing, which is 6. Correct? So I'll get you started. So alternative approach, even though they didn't ask for it. Alternative approach, using the fundamental theorem of calculus part 1. That integral from 0 to 12 fx dx, since the function changes, right? It changes from this branch to this branch at 6. So I'm gonna go from 0 to 6 of the function fx plus from 6 to 12 fx dx, right? Correct? This is by property 6 above. I can split and I can stop at any point. I choose the point to be 6. Okay, what's f of x between 0 and 6? What's the function f of x between 0 and 6? Well, the function f of x, as long as you are less than 6, in particular between 0 and 6, is negative half x plus 9. So that's gonna be negative, that's gonna be negative half x plus 9. Correct? Why? Because the function here it corresponds to x being between 0 and 6. For x between 0 and 6, as we said, for x between 0 and 6, for any x less than or equal to 6, the function f of x is that guy. So you can take this function out, replace it by this. Now, for x bigger than 6, so for x between 6 and 12, what's f of x for x being between 6 and 12? For x between 6 and 12, the function f of x is now 6. Correct? As you see on the picture, now we are at height 6. The function is a constant now. Right? So this becomes the integral. So the integral from 0 to 6 minus half x plus 9 dx plus the integral from 6 to 12. And the function here, I forgot to label it. This function now here is 6, right? So we get 6 dx. Correct? You know what? I changed my mind. I want to continue this just for you to be able to see me doing it again. All right, let's split this. Right? One of the formulas, one of the properties we know is that at the integral commutes with addition, so I can split addition. So this becomes 0 to 6 minus half x plus, or dx plus integral from 0 to 6, 9 dx plus the integral from 6 to 12, 6 dx. Agree with this so far? Okay, let's find each one. Minus half is a multiplicative constant. Push it outside. You get minus half primitive or integral from 0 to 6 x dx plus, let's do these guys. These are, each one is a pure constant. Or you know what? Let's keep it. But we'll do everything in the next step. 9 dx plus 6 to 12, 6 dx. Okay? All right. Now we're gonna find a primitive function for each of the following integrand: x, 9, and 6. Can you find for yourself a primitive function for x? That's x squared over 2, right? X squared over 2. Okay, so how about as we used to do above, how about we call the function primitive, the primitive function for x, how about we call it f of x? So that's x squared over 2. How about the primitive function for 9? Call it g of x. That's gonna be 9x. Again, don't worry about the constant because of the fundamental theorem of calculus. You're gonna evaluate it at the top minus the evaluation of this primitive at the lower, and the constants are gonna cancel. So let's, from the get-go, take the constant to be 0. And how about the function, the primitive function for 6 to be called h, and this is gonna be 6x, right? So this becomes equal to f, oops, I forgot the minus half. So minus half times f of the upper bound 6 minus f, an antiderivative of x, which is f, at the lower bound 0. Correct? Plus primitive of 9 was found to be 9x, so g of the upper bound 6 minus g at the lower bound 0. And finally, plus 6, primitive of 6 was h at the upper bound 12, minus h at the lower bound 6. You agree with that? Okay. I'm gonna adopt a notation. Instead of writing all this thing every single time, how about we find a notation for all these writings? So how about the following notation? How about the following notation? Instead of writing all of this, I'm gonna erase all this guy, all the brown thing that you see on the screen. I'm gonna erase it and replace it by the following. The minus half is gonna be there because of this constant minus half, and that function, the antiderivative of f, the antiderivative f of x was found to be x squared over 2, and this is an antiderivative, it's not v. We took the constant to be 0. So the way I'm gonna do it, I'm gonna take it between brackets, I'm gonna write it, and I'm gonna write the bounds here. What are the bounds? 0 to 6, right? 0 to 6. And what this means, it means exactly this. So it means that function evaluated at 6 minus that function evaluated at 0. It's just a notation. Instead of writing f of x equals that, g of x to be that, and so on, you can just take the function f, which is x2 over 2, and then decorate it by 0 and 6, and the understanding is what this means. This is a notation for this guy evaluated at 6, so f of 6, and this guy evaluated at 0, so f of 0. Okay, you're gonna see it how it's gonna unfold. This is a universal notation. Everyone writes it this way. Plus, for this guy, what's a primitive for this guy? 9x, right? So 9x, and that's the bounds are 0, 6. And what's a primitive for 6 is the h, so it's a 6x, and this is between 6 and 12. And as I told you, what this notation means is negative half times that guy evaluated at the upper bound, right? It's f of 6, so that guy evaluated at the upper bound, so 6 squared over 2, right? Minus that guy evaluated at 0, so 0 squared over 2. Makes sense? Again, this is just a notation for such a thing. This is a notation for this thing, and this is a notation for this thing. So instead of writing all of that, I see a mistake. I don't need the 6 here. I don't know why I wrote the 6. I don't need the 6. Okay. So one more time. I don't know why this is not erasing everything at once. All right. So one more time. This notation here with the brackets with the upper and lower bound, it only means an antiderivative evaluated the upper bound minus the antiderivative at evaluated the lower bound. Okay, so it means that. And the next one, what is this? This is this guy evaluated at 6, so 9 times 6 minus 9 times 0. Okay, plus this guy, this function evaluated at 12, it used to be h, right? This function used to be h, evaluated at 12, so 6 times 12 minus 6 times 6. Do you agree with me? So evaluation of this guy at the upper bound minus the evaluation of this guy at the lower bound. Okay. All right, and how about you complete the algebra on your own? So anyway, so 36 divided by 2 here, you complete the algebra. What you should get, you know what, since we know the answer, so let's compare it. Minus 1/2 36 over 2 minus 0 plus 54 minus 0 plus 72 minus 36, right? Because 6 times 12 is 72. Okay. So that's minus 1/4 of a 36, and what's 36 divided by negative 4? It's negative 9, right? Plus 54 plus this is 36, correct? And 54 plus 36, this is 90, minus the 9, which is 81. And I'm pretty sure we found 81 before, right? What was it? Yeah, it was 81. Okay. So that's a different approach. Let's summarize the approach. How did we treat this? Because the function changes, I mean, it's still the name of the function is f of x here, right? Still f of x. But f of x is a piecewise defined function, so the recipe of f changes, right? So the function changes at 6. As such, I'm gonna split. Since 6 occurs on this interval of integration 0 to 12, I'm splitting that at 6 and replacing what f of x means in between 0 and 6. It meant minus half x plus 9. And replacing what f of x means between 6 and 12. It meant 6. And then I integrated, right? And we introduced a notation. Instead of writing this whole brown thing here, typically people write this notation. This is just a notation for, or abbreviation for that writing. Okay, so instead of explicitly listing what an antiderivative of x is, 9, and so on, you find it. I mean, primitive of x is x squared over 2. You find it and you put the bounds. And the understanding is when you write such a thing, you mean this function evaluated at the upper bound minus this function evaluated at the lower bound, right? Each time you write such a thing, it means evaluation at the upper minus evaluation at the lower, and so on and so forth. Okay? Very good. All right, let's move on to, I'm gonna move on to the book, but to a different page. Namely, let's go to page 292, section 4.4, and let's do one of these problems from, or a few problems from 9 through 36. The question is to evaluate the definite integral. And let's start by 22. So we're gonna integrate the function 6 minus t square root of t dt, and we're gonna integrate it between 0 and 2. Okay. So that's on page 292. And this is number 22. So we're integrating between 0 and 2 the function 6 minus t square root of t dt. Realize that the function here is not a line, right? This is 6 minus t times square root of t. This is not a line anymore, so the geometrical form, the geometrical shape that we're going to be getting, and by this I mean the region bounded by the function, the x-axis, and the two vertical lines x equals 0 and x equals 2 is not as nice as we used to do, or we used to encounter before. We used to have either a triangle or a rectangle or a circle, right? So over here it's neither a triangle nor a rectangle nor a circle, right? This is a function which has a shape different than one of these just mentioned. Okay, as such we have to use the fundamental theorem of calculus in this context. Okay, all right, so how do we do this? So we're gonna try to find primitive here, primitive function of this integrand. It's not that easy yet, right? How about we distribute the multiplication over subtraction? We have the multiplication here. How about we distribute and then split the integral, because it's gonna look like 6 square root of t, right? 6 square root of t minus t square root of t. So this becomes the primitive of a difference, and primitive of a difference is the difference, I didn't mean primitive, I mean definite integral of a difference. This is going to be the definite integral of each one of them, right? So minus integral from 0 to 2 t square root of t dt, right? Okay, 6 is a multiplicative constant. You can push it outside. You get the integral from 0 to t. Square root of t is t to power half, right? Square root of t is t to power half dt minus the integral from 0 to 2. Square root of t, we just said, it's t to power half times t to power 1. Well, t to power half times t to power 1 is t to power 3 halves dt, right? Okay, very good. What's the primitive of t to power half? Well, primitive to t power half is t to power half plus 1 over half plus 1. Remember this from an earlier section? And then we're gonna now evaluate it between 0 and 2. Remember what this notation means? This is an abbreviation to the following. It's that guy evaluated at 2 minus this guy evaluated at 0, right? Fundamental Theorem of Calculus Part 1 here. Minus the primitive of t to power 3 halves, which is t to power 3 halves plus 1 divided by 3 halves plus 1. And this is between 0 and 2. Same thing. That means, this whole thing here means that guy evaluated at 2 minus that guy evaluated at 0. Okay. What's half plus 1? Half plus 1 is 3 halves, so this becomes t to power 3 halves, correct? Dividing by 3 halves is the same as multiplying by 2/3. Between 0 and 2, minus, same discussion here, but 3 halves plus 1 is 5 over 2. Dividing by 5 over 2 is the same as multiplying by 2/5. T to power 5 over 2, right? Between 0 and 2. Okay. And as we said before, this means 6 times that guy evaluated at 2. Certainly I can push the 2/3 outside here. How about we do it? So we can push the 2/3 outside. So this becomes 6 times 2/3, right? 6 times 2/3 times t to power 3 halves, evaluated at 2. So this becomes 2 to power 3 halves minus this guy, without the 2/3 because I pushed it out. This guy evaluated at 0, so this is 0 to power 3 halves, which is 0, minus 2/5. This guy evaluated at 2, so 2 to power 5 over 2, minus this guy evaluated at 0, which is 0 to power 5 over 2, which is still 0, right? Okay. Alright, how much is this? How much is this? 6 divided by 3 is 2. 2 times 2 is 4. That's the, that guy is 2, right? This guy is 4. Times, this is 0, so this whole bracket, or the value of this group is 2 to power 3 halves. And what's 2 to power 3 halves? What's that guy? Well, take a look. This means the square root of 2 cubed, right? This means the square root of 2 cubed. Alright, let's keep it like this for a second. Minus 2 over 5 times this, the value of this package is square root of 2 to power 5, right? Correct? Remember the something to power m over n is the same thing as the nth power of the thing to power m. Correct? Remember this? So that's exactly what I'm using here. Alright. So then we get square root of 2 cubed is 2. Square root of 2 cubed is 2 square root of 2, right? Minus 2 over 5 times, how much is this? 2 to power 5. 2 to power 5 can be thought of as 2 to power 4. Square root of 2 to power 4 is 2 squared, so 4 square root of 2. Am I correct? Alright, so this means what? This means 8 square root of 2 minus 8 over 5 square root of 2. Okay, and if you do the same denominator here between 8 and 8 over 5, this is 40 minus 8. 40 minus 8 is 32 over 5 square root of 2. I hope I didn't do any algebraic mistake, but that's the idea. Okay. All right, so what do we get? This guy, this definite integral is equal to this, is equal to this. Okay. So the net area of the region bounded by this function 6 minus t times square root of t, right? So the net area of the region bounded by this, the x-axis, and what? The two lines, the two vertical lines, x equals 0 and x equals 2. So that area happens to be, that net area happens to be 32 over 5 square root of 2. Okay? All right. Let's go back to the book. How about doing 27? So the integral from 0 to 4, absolute value of x squared minus 9 dx. So 27. The integral from 0 to 4, absolute value of x squared minus 9 dx. Okay. What's x squared minus 9 in absolute value? So let's have a small discussion on this side here. What's absolute value of x squared minus 9? Well, this means two things, right? Depends whether the guy inside the bars is positive or negative. This means two things. It means x squared minus 9 if that guy is or non-negative. Okay, let me keep moving a little more. So if this guy is non-negative, that means minus this guy if this guy is negative. Correct? And when is this guy, when is x squared minus 9 non-negative? If you unravel what this means, well, this means this is the same thing as saying x is less than or equal to negative 3, or x is greater than or equal to 3, right? So if this happens, that's exactly when this happens. So these two are the same. And what does this mean? X squared minus 9 is negative. This means that x is between minus 3 and 3. Correct? Let me give you more insight into why this is the case. Let me give you more insight into the matter here. Look, how do you graph x squared minus 9? How do you graph x squared minus 9? It's the parabola x squared shifted down by 9 units, right? Shifted down by 9 units. So we're talking about this function, something like this, right? Okay, that's a bad one. Let's try again. So it's the function, it's the parabola shifted down by 9. This is x squared minus 9. And what are these intercepts? It's when this function vanishes. Well, where does this function vanish? At minus 3 and 3. Right? This is 0 if and only if x is plus or minus 3. So at these points, right? Okay. So you see the function x squared minus 9? I'm talking about these two conditions here. Let's focus on one of them. Let's focus on this. X squared minus 9 bigger than or equal to 0. I'm talking about this function, this parabola. Where is this parabola 0 or more? Where is it at or above the x-axis? Well, here and here, right? Correct? So, and these branches to which x they correspond? They correspond to those x's which are from minus infinity to minus 3, so less than or equal to minus 3, or bigger than or equal to 3. That's exactly what I wrote here, right? And similarly here, x squared minus 9, I need this function, what this means, this inequality means that the function, the parabola, is less than 0, which means it's below the x-axis. What is it below the x-axis? We're talking about this part. We're talking about this part, right? And this is when x is between minus 3 and 3, right? This is what I wrote. Make sense? All right, so now we have some insight into this. What do we need? We need to integrate from 0 to 4 that function. And between 0 and 4, 3 is between 0 and 4, right? Remember, this function, absolute value of x squared minus 9, switches at 3 and at negative 3, correct? It jumps from one to the other. 3 happens to be between 0 and 4, so this function is going to change from being that to that, right? Between 0 and 3, the function is going to be between 0 and 3, the function is going to be this one, right? Because between 0 and 3, I'm talking about values here. The function is going to be minus x squared minus 9. And from 3 to 4, so once you pass 3, you're talking about the function being this. Okay? So since the function changes recipe at 3, I'm going to make a split as we used to do before at 3. Okay? So that function, this function, which is the integral from 0 to 4, absolute value of x9 minus x squared minus 9 dx, is equal to the integral from 0 to 3 x squared minus 9 dx plus the integral from 3 to 4 absolute value of x squared minus 9 dx. Correct? Why did I split? I mean, I can split no matter what, but I chose 3 because the function absolute value of x squared minus 9 becomes something, I mean, it changes recipe at 3, right? We just talked about that. We change this recipe at 3, this absolute value function. Okay. All right. And what's the recipe within each interval? From 0 to 3, what's the recipe of this guy? From 0 to 3? The recipe of this guy is minus x squared minus 9, right? It's minus x squared minus 9. Why? Because this guy here is negative in between 0 and 3, right? In between 0 and 3, this guy is negative. As such, the absolute value is going to turn it into positive, and it's going to inject a minus sign. And this means 9 minus x squared, right? The opposite of x squared minus 9 means 9 minus x squared. Okay. And how about this guy now? And I mean, this integrand, I'm talking about now x being between 3 and 4. X being 3 and 4, so it's bigger than 3. X is bigger than 3. And if x is bigger than 3, the absolute value function, x squared minus 9, is x squared minus 9. Because x squared minus 9 is positive now, or non-negative. So this guy now is x squared minus 9. Okay. So it depends where x lives. It's going to tell us what the absolute value of x squared minus 9 is. If it lives from 3 to 4, then the absolute value of x squared minus 9 is x squared minus 9, because x squared minus 9 is non-negative. And if it lives between 0 and 3, if x lives between 0 and 3, then the absolute value of x squared minus 9 is going to be the opposite of x squared minus 9, because that guy is negative now, and as such I get 9 minus x squared. Okay. So that tells us then that this is equal to the integral from 0 to 3 of 9 minus x squared, right? Talking about this guy, 9 minus x squared dx plus the integral from 3 to 4 x squared minus 9 dx. You agree with that? Okay, very good. We can split, because this is an integral of a difference. Or, I mean, I can think about this whole thing as a function, and I want to try to find an antiderivative of it. I want to try to find a primitive function of this. What's a primitive function for 9 minus x squared? Isn't it? Or can't you think about primitive of 9, which is 9x, minus primitive of x squared, which is x cubed over 3? Correct? If you don't want to do it this way, you can split. and this is gonna be between 0 and 3, between the bounds 0 and 3, plus same thing I'm gonna do here. Primitive of x squared minus 9 is a primitive is x cubed over 3 minus 9x. And this is between 3 and 4, right? Makes sense? Okay, so then I'm going to evaluate at the upper bound, subtract the evaluation of the function at the lower bound. So let's evaluate this primitive function at 3. So what do I get? 9 times 3 minus 3 cubed over 3, right? So this is the evaluation at the upper bound minus the evaluation at the lower bound. What's the evaluation at the lower bound? It's going to be 9 times 0 minus 0 cubed over 3, right? 0 cubed over 3 plus this plus. Same thing here. I'm going to take this guy evaluated at the upper bound 4. So 4 cubed divided by 3 minus 9 times 4. This is the evaluation at the upper bound minus the evaluation at the lower bound. So I'm going to replace x by 3, right? So I get 3 cubed over 3 minus 9 times 3. Alright? Okay, and this is algebra now, so alright. This is what? 9 times 3 is 27. 27 minus 3 cubed over 3 is 3 squared, which is 9, minus 0, right? So all this is simply that guy then, plus, let's see here, 4 cubed, so 4 cubed is 4 squared, so 16 times 4, 16 times 4 is 16 times 2, which is 32 times another 2, so 64 over 3 minus 36, right? Minus 36 minus this guy, right? Minus this guy. And how much is this guy? It's very similar to this, right? That guy is 3 squared, so 9 minus 27, right? Okay. So I get 27 minus 9 plus 64 divided by 3 minus 36 minus 9 plus 27. 9 minus 27, so with the opposite sign becomes like this. Alright, this is algebra now again. 27 times 2, 54, minus 9 times 2, 18, minus 36 plus 64 over 3, which is equal to, what's 36 minus, what's minus 36 minus 18? This is 54. So 54 minus 54, they cancel each other. This is simply then 64 over 3. Correct? Because all this is 0. So 64 over 3. Okay, so what's the conclusion then? This integral is 64 over 3. Now what's this integral? This is the integral that, this definite integral means it's the net area of the region bounded by the function absolute value of x squared minus 9 on the x-axis and the two vertical lines 0, x equals 0 and x equals 4. Okay, and that function is non-negative, right? So it's the area under the curve. What's this function absolute value of x squared minus 9? We have half of it actually. Half of it is here. Absolute value of x squared minus 9 is very similar to this. With what? So absolute value of x squared minus 9. It's that guy when x is minus less than minus 3 and less than or equal to minus 3 and bigger than or equal to 3. So that guy is the same thing as this branch and this branch. But when it comes to the middle piece, which means when this guy is negative i.e. when x is between -3 and 3, so we're talking about those y values, what happens? This function now is going to take the opposite of that piece. And what does it mean, the opposite of that piece? Opposite of that piece, every point is going to have its opposite, so it's going to be above the x-axis. So we're talking about this, correct? So what's the function square root of x squared minus 9? It's that, this, and this, right? So like this, something like this. And what's that area that we are talking about? The area from 0 to 4, this is the vertical line x equals 0. Somewhere here is the vertical line x equals 4, right? And we're talking about this area then. Talking about this area. Correct? And you see this area here, I mean, it's not, as we described before, this is not easy to find except if you integrate, if you do fundamental theorem of calculus, because the curvature here is not a line. It's not a line, so this is not a triangle. This is not a triangle, right? The curvature of this boundary is different than being, is not a line. So all technique, like in the previous section, doesn't work. We have to appeal to the fundamental theorem of calculus. All right, so our work here showed that this area that you see, this shaded portion or area that you see, is actually 64 over 3, right? So it's 64 over 3. It's certainly positive. The net area is positive because the function is above the x-axis. So that looks good. All right, let's keep going. Let's do one that has to do with trig functions. How about 32? So we're going to integrate the function secant squared theta divided by tangent squared theta plus 1. And the integration is going to occur between 0 and pi over 4. Okay. So 32. We're integrating between 0 and pi over 4 the function secant squared theta divided by tangent squared theta plus 1 d theta, right? Okay. Well, what do we know here? Tangent squared theta plus 1, this is equal to, it's one of the Pythagorean identities that you learn in trig. If you forgot them, don't worry, let's just do it again. This means sine squared theta plus 1, sine squared theta divided by cosine squared theta plus 1, right? So sine squared theta divided by cosine squared theta plus 1, because tangent is sine over cosine, right? And if you do the same denominator, we get sine squared theta plus cosine squared theta divided by cosine squared theta. And this is what? What's upstairs? It's 1, right? Upstairs is 1. And downstairs is cosine squared. And this is secant squared, right? So downstairs is simply secant squared. So secant squared over secant squared. Okay. So 0 to pi over 4, secant squared theta over secant squared theta d theta. But this is 1, right? So this is integral from 0 to pi over 4, 1 d theta. And what's a primitive for 1? It's theta, right? And this is between 0 and pi over 4, you evaluate it. So this is simply pi over 4 minus 0, which is pi over 4. Correct? So, okay, this wasn't that hard. I thought it's going to be a little harder. So let's do another one. Let's do 30. So we're integrating 2 plus cosine x between 0 and pi. So 30. Let's integrate between 0 and pi the function 2 plus cosine of x dx. Okay, well, this is the same as the integral from 0 to pi 2 dx plus the integral from 0 to pi cosine x dx. And what's a primitive of 2? The variable should be x, so it's 2x, right? And taken between 0 and pi plus what's a primitive of cosine? So what's a primitive of cosine? It's sine of x between 0 and pi. Okay. Let's evaluate this at the upper bound, which is pi. So this means 2 pi minus, evaluate this at the lower bound, so 2 times 0, so 0, plus evaluate this at the upper bound, sine of pi, minus evaluate this at the lower bound, which is sine of 0. Okay, and this is 2 pi. Why? Because this guy and this guy are both 0, right? Sine of pi and sine of 0 are both 0. So as such, we get 2 pi, right? All this is 0. Okay. Okay, let's go to the next page. How about we do one of these problems? How about 64? Actually, how about 66? It's the same, but here it's trig. Let's do 66. What's the question here? Find f. It's given. Find f as a function of x and evaluate it at x equals 0, x equals pi over 4, and x equals pi over 2. Okay, so let's find it first and then evaluate it. I have f of x equals minus or integral from minus pi to x sine theta d theta, right? So that's number 66. We have the function f of x is equal to this, right? How about we find it, which means we integrate, let's integrate that guy. What's a primitive of sine theta? Primitive of sine theta is negative cosine theta. This is between negative pi and x, correct? And this is equal to, we evaluate this at the upper bound, so negative cosine of x. We chip away from that the evaluation of negative cosine theta at negative pi. So like something like this, right? Correct? So one more time, it's this guy evaluated the upper bound minus this guy evaluated the lower bound, right? The lower bound is minus pi, so we get this. All right, and let's help each other here. So minus times minus is plus, right? So this is plus, and cosine of negative pi, cosine is an even function, that's cosine of pi, correct? Cosine is an even function, so that's cosine of pi. Let me make it more legible. So cosine of pi, right? Because cosine is an even function. I'm talking about just this piece, right? This piece. So this becomes negative cosine of x minus times the minus is plus cosine of pi. Agree with that? Okay, what's cosine of pi? Oops. What's cosine of pi? Is negative 1. So f of x at the end of the day is this guy. Correct? And this is for any x. This is for any x. In particular, they want to evaluate this function at 0, pi over 4, and pi over 2. Let's do it. So they want f of 0, they want f of pi over 4, and I want f of pi over 2. Okay. All right. F of 0 means negative cosine of 0 minus 1. And what's cosine of 0? Cosine of 0 is 1, so this is negative 2, correct? Cosine of 0 is 1. So this becomes negative 1 minus 1, which is negative 2. Let's move on. The next one is f of pi over 4. So it's going to be minus cosine of pi over 4 minus 1. And what's cosine of pi over 4? Square root of 2 over 2. So that's minus square root of 2 over 2 minus 1. And this is as good of an answer as anything. If you want to take the same denominator, be my guest. F of pi over 4 is minus cosine of pi over 2 now. Pi over 2 minus 1. But what's cosine of pi over 2? What's cosine of pi over 2? That's 0. So negative 0 minus 1 is negative 1, right? So we get this. Okay. All right. Next. Let's go to these problems between 75 through 80. Between 75 and 80. So the question here, use the second fundamental theorem of calculus to find the derivative of this given function. Okay. How about we do 80? So I want to differentiate this function, integral from 0 to x. X is the variable, right, for the function capital F. C cubed t dt. Okay, so I have the function, this is on page 294, and this is number 80. So I have f of x equals integral from 0 to x sec cube t dt. Okay. Let's revisit the fundamental theorem of calculus part 2. Let's see what it says. It's right there. So that's what I'm alluding to, this one. So if you have a function g of x, which is equal to the integral from a to x, f of t dt, f is supposed to be a continuous function on this closed and bounded interval a, b, right? So if you take an x between a and b, then this function that just defined as such is continuous on the closed and bounded and differentiable on the interior of that set. And moreover, the derivative of this function g at x is equal to this function, this integrand f at x, correct? So that's what we're gonna be needing in this problem. Okay. Very good. Keep in mind that here x is, sec of t. Remember, sec means 1 over cosine, right? 1 over cosine, and cosine is not defined. The very first point where it's not defined after 0, the very first point where it's not, where secant is not defined, is where cosine is 0. And cosine is 0, again, I'm talking about the very first point after 0, where cosine is 0, as pi over 2, right? So what I'm saying is secant of pi over 2 is not defined. So secant cube of pi over 2 is not defined, because secant means 1 over cosine, and cosine is 0 at pi over 2. As such, that function is not defined at pi over 2. And it's not defined at pi over 2 plus k pi, where k is an integer. My point is, x here should be between 0 and pi over 2, open pi over 2, right? Okay. All right, so you don't have to talk about this anyway, but I'm just completing the picture, if you will. All right, you get what? We want to differentiate this function with respect to x, right? And differentiating this means differentiating this with respect to x by the fundamental theorem of calculus part 2, right? Fundamental theorem of calculus part 2 tells us that this is nothing more than the function f of t, this is f of t in our discussion. It's this function evaluated at x, right? If you revisit the second part of the fundamental theorem of calculus, it means f of t evaluated at x, so it's f of x. And what's f of t here? It's c cubed. Evaluate this at x, you get this. Correct? So it tells us that f prime, this is f prime, is equal to c cubed of x. Make sense? Okay. I mean, you can do all of these quickly now. For example, this, the previous one, f of x is the integral from 1 to x square root of t cosecant of t dt. If x is given appropriately, and by appropriately I mean by making the function square root of t cosec of t on the interval 1 comma a number to be continuous, then the derivative of this capital F at x is going to be square root of x cosecant of x, right? Makes sense? Over here, 78, let's say. F of x is integral from 1 to x fourth power t dt. For any x bigger than 0, in particular bigger than or equal to 1, this function, fourth root of t, is going to be continuous on any closed and bounded interval that starts at 1 and ends at any point after. That function, square root of the fourth power of t, is continuous, and the derivative by the second part of the fundamental theorem of calculus, the derivative of capital F is simply fourth root of t evaluated at x, which means fourth root of x. Okay, so f prime of x is fourth root of x, and so on and so forth. Okay. All right, more interesting is the next group. Let's do how about 80? Let's do the last one, 86. Okay, let's do 86. So f of x is the integral from 0 to 2x cosine of t to power 4 dt, and still we want to find f prime of x. Okay, this is 86. We have f of x equals the integral from 0 to 2x cosine of t to power 4 dt. Okay, and what do they want? They want f prime of x. That's what they want. Well, here I don't have x here, right? Like I used to before. I used to have x. And the fundamental theorem of calculus deals with x here, right? But we can extend it. We're going to see how. Just bear with me for a second. This means what they want is they want the derivative of f with respect to x, right? But if you call this variable something else, how about we call it, not this variable, how about you call this function u? This is a function of x, right? This is a function of x, and this is a differentiable function. 2x is differentiable. So as such, I can use the chain rule. I can use the chain rule to continue this. Because, look, f now is a function of u, which in turn a function of x, right? F is a function of u, this is u now, which in turn is a function of x. So if you want to differentiate with respect to the ultimate variable, which is x, differentiate the function f with respect to u, and then multiply by the derivative of u with respect to x. Right? This is chain rule here. This is chain rule here. One more time. Chain rule. Right? Okay. And this is equal to differentiate the function f with respect to u. So this is then equal to, let me write this here. So that's derivative with respect to u of f. And what's f? What's f? It's that, right? 0 to u, right? 0 to u cosine t to power 4 dt. times the derivative of u with respect to x. You agree with me? You see this? And now look at this. That guy here is this guy here, right? And this is the format of the fundamental theorem of calculus part 2, correct? Let me convince you one more time. You see here? That's what I was alluding to. It's that guy, the same guy that sits here and here, right? It's the same guy that sits here and here. As such, this is simply f evaluated at x, correct? All right, let's go back to the page. We get what? We get that this is equal to, as we said, that guy evaluated at this number. And what's this number? It's the u guy, right? So cosine of u to power 4 times the derivative of u with respect to x. How much was u? It was 2x. So this is the derivative of 2x with respect to x, right? This guy is the derivative of 2x divided by with respect to x. Why? Because u is 2x. That's what u means. Okay, so then this is cosine of u to power 4. So how much is u again? It's 2x times the derivative of 2x with respect to x. That's 2. Okay. So then we get 2 cosine 2x to power 4. Okay, and sure you can, you can simplify this, or you can, what's 2 to power 4? 16. This is 16x4 then, correct? So this would be the derivative of the function, of this function. Okay. All right, let's do one last one. How about 81? Okay, so I still have to differentiate this function. F of x equals integral from x to x plus 2 for t plus 1. So 81, f of x is the integral from x to x plus 2 for t plus 1 dt. Okay. As you see here, I have x plus 2. I don't have the format of the fundamental theorem of calculus part 2. What I'm going to do is I'm going to split this, because if you remember the fundamental theorem of calculus part 2, let's go back there one more time. One of the bounds is a pure constant, right? One of the bounds is a pure constant. You see? One of the bounds is a pure constant, correct? So let's, over here I don't have a pure constant in my current situation. I'm gonna split. I'm gonna split somewhere. I can choose any number, because 4t plus 1 is continuous everywhere. It's a polynomial. How about 0? Let's go for 0. So integral from x to 0, 4t plus 1 dt plus integral from 0 to x plus 2, 4t plus 1 dt. Agree with that? Okay. And this is equal to, if you want to reverse the bounds, you pay price minus. Remember this property? It's one of the properties we talked about, or we revisited over here. I'm talking about property 5, right? If you reverse the bounds, then you pay price minus. Okay. All right. So let's do it. So let's reverse the bounds here, and I get 0 to x. I pay the price minus 4t plus 1 dt plus 0 to x plus 2, 4t plus 1 dt. Yes? Okay. And then what? And then what? What do we want? We want f prime of x. We want f prime of x. And f prime means differentiating with respect to x in this context, yes? All right. Which means I'm differentiating with respect to x all this guy, all of this guy, right? Agree? Okay. Which means I'm gonna differentiate the first guy plus I'm gonna differentiate the other because the operator d over dx is linear. It allows me to push out multiplicative constants and to split sum or differences, right? So here this is the same as opposite of the derivative with respect to x of this guy, 0 to x 4t plus 1 dt plus the derivative of this guy, which is 0 to x plus 2 4t plus 1 dt. Okay. All right. And look here, this is by the fundamental theorem of calculus. I'm talking about this part. By the fundamental theorem of calculus, part 2, this is this function evaluated at x, right? This function evaluated at x. The derivative of this whole integral with respect to this x is equal to this guy evaluated at x. And what does it mean? This means 4x plus 1. Agree with that? Evaluate this at x. This is 4x plus 1. All right. How about the other one? How about the other one? How about this guy? Well, here I don't have x. I have x plus 2, which is a function of x. So I can think about this as u and treat it as in the previous problem. Correct? So what I get here is I'm differentiating with respect to u this integral, 0 to u 4t plus 1 dt, right, times derivative of u with respect to x. And what have I used here? I used the chain rule, exactly as I've done above. And by above I mean the previous problem. Problem what, 86 was? Yeah, this one, right? The chain rule, because this bound is a function of x. I don't have x. I don't have that guy that I'm differentiating with respect to, right? I have a function of it. Well, chain rule can handle it. Okay. So I'm here then. And then what? Now I have this format. I have this guy and this guy the same, right? The same one. And now the fundamental theorem of calculus part 2 kicks in at this point. And what do I get? I get the evaluation of this guy here, add this upper bound, which was u, right? So 4u plus 1 times the derivative of u with respect to x. So the derivative of u with respect to x, which is x plus 2 in my case. I'm differentiating u with respect to x, so I'm differentiating x plus 2 with respect to x. Okay, this is 4 for u, but we just said u is x plus 2 plus 1, and this whole thing is gonna be multiplied with the derivative of x plus 2 with respect to x, which is 1, right? If you differentiate x plus 2 with respect to x, you get 1. Okay, what is this green thing? This is 4x plus 4 times 2, which is 8 plus 1, so this is 9, right? Agree with that? 4x plus 8 plus 1 is plus 9. Okay, so then back to the purple guy. This is equal to minus what we found here, which is 4x plus 1, plus the green guy, which is 4x plus 9. Correct? And if you subtract 4x plus 1 from 4x plus 9, the 4x is cancelled and this becomes 9 minus 1, so that's 8. Okay? All right, this completes this section.